All right, let's give Paul a warm welcome. Can't wait for this.
Oh. Yeah, you're clapping now. Okay. So thanks, as everyone else has said, thanks so much to the organizers to putting this together. It's been very nice seeing old friends and friends who are also home. And meeting new people also, and having new ideas, which is always great. That's it. I haven't been to a workshop like this in quite a while, where it's one topic, really quite concentrated. It's really very nice to then be able to follow all the talks and think about them, and so I really appreciate that. So as most of you know, I have a habit of changing my titles, and so this first change is what we're doing. Let's see, is that not going to work? There we go. Okay, so I will explain why I prefer the term quantum interrogation, although I'll later on say, well, maybe that's not such a good term either. Okay, so just actually, none of the people on this picture are involved in anything that I'm going to be talking about. But anyway, it is a current photo, and it's a chance to advertise that we're always looking for new students and postdocs, and also collaborators. We won't force you to dress up. But anyway, hopefully other collaborations will spring from this meeting. So the title was looking back, looking forward, and looking sideways. So it's looking back. So obviously, I don't need to actually go into the motivation for why we might be interested in interaction-free measurements or quantum interrogation, although this is kind of a funny cartoon. And of course, the solution that was proposed now 30 years ago, where we have a precondition of an interferometer that's set up a particular way, which we can then spoil that interference. And that spoiling of the interference gives us information some fraction of the time, not all the time. And we already know that we can, there are ways that we can improve upon that. So I'll just a little historical thing. So I was at a conference, and I'm pretty sure it was in France somewhere, but I can't remember exactly which conference it was. And I was kind of sitting in the back, and I'm pretty sure, Lev, you were the person who was presenting this idea. And I remember the feeling of the crowd, because there's like a wave that went from the front to the back of the room and then washed back up. And it was actually two waves. The first wave was, oh, this is impossible that this can work. And then it rushed back up. And then the second wave was, oh, this is obvious. And it rushed back and then rushed back up. And I thought it was an incredibly cool idea. I certainly was gripped by it. And so I was, at the time, I think I had not yet gone to join Anton Zeilinger for my postdoc position. Maybe it was Vienna. Could have been that. Were you in Vienna in like 1993?
There is one event. It was in Boston, and we had beer, you, I, and Anton. And you promised me that you will do the experiment.
Okay, but I do remember seeing it announced at a conference as well. So yeah, we wanted to see if we could demonstrate this, and then so we could do this at the photon level. It's really the only way you can claim that it's going to be interaction free. Certainly, if you have a classical wave that's going both paths in the interferometer, turns out a little easier to set up with a Michelson than with a Mach-Zehnder interferometer. And so we wanted to both be able to do a simple demonstration of it, although we knew that wouldn't necessarily impress people too much. But the fact that we're able to detect the presence of this object basically by canceling out the interference, that was the basic principle. And then we'll come to the advanced version in just a little bit. And then we also investigated this phenomenon of, well, if we change the reflectivity of the beam splitter, as we've already seen, we can improve the efficiency. So nominally it's 25% efficiency, but if you can do some recycling, if you're at the 50% level, then you can get that up to 33%. And if instead you change the reflectivity of the beam splitter, you can then push that efficiency higher. But it does come at the cost that the probability of making the interaction-free measurement starts to drop. And that's maybe not so good if you're doing a system, a practical system where, for example, you want to do some imaging because you have noise on the detector, and as we heard from the previous talk, the noise on the detector then eventually starts to dominate over the signal that you're looking at, and then that's not so useful. So there's, in general, some kind of an optimal spot. That this is, by the way, why the efficiency here was dropping. It's because there's noise in the system. There's always going to be some noise from something or other. So we did then a couple of years later implement this as an imaging system. And the main reason I want to go through this, I guess there are two reasons. One is to introduce just kind of a different way of the different modes. Now I'm going to be talking about polarization. So we're going to start out with 45-degree polarized light. One of these things have a laser pointer. It's almost a quantum laser pointer. People actually see it?
Yeah.
Okay. So I have 45-degree polarized light. It gets split by polarizing beam splitters into the horizontal and the vertical component, and they meet up with each other, and it's set to keep the phase the same. So incident 45-degree polarized light will always go out to detector D1. But if I can instead block the vertical path, then I only have horizontally polarized light here. Sorry, this is designed to polarizing beam splitters set to be reflecting 45-degree polarized light and transmitting -45, or effectively doing that with some sort of weight plate in front of it. And if instead I block one component, say the vertical component, I only have the horizontal, and then it equally shows up at both detectors. So this is equivalent to the other interferometer, but it's using polarization instead. And we then investigated, well, if I can put some focusing elements in, I can get a small spot, and then in principle, I can raster scan through, just as we heard in the previous, and I can get some kind of an imaging information. And so, okay, so this is everything I was saying. In principle, or actually in practice, you can focus it down to of order micron, or the wavelength of light. You can get quite good spatial resolution. And so we looked at a number of different things. This was one of my arm hairs, so they're pretty narrow. They're only about 40 microns across. And what we're showing here is the directly measured transmission of the as I scan the position of the hair. So when the hair is off to the side, then I have a high transmission here, transmission 1, and then when the hair comes in, then the transmission drops, and then it comes back up. Now notice it doesn't actually ever drop to 0, so it's always at least partially transmitting. And also has some kind of weird effects. If you look at the far field, it turns out the hair, my hair in particular, because it's fairly straight, is tubular and it's transparent, so it's like a cylindrical lens, and so that actually screws up the optics in ways that is quite confusing initially, because it's not an opaque thing. In any event, and then what's shown in purple is basically the dark point of the interferometer. When the hair is in place, then in fact we're getting a signal. So we're detecting this object, in this case the hair, with less than 1 photon, and getting some kind of spatial resolution. But it's kind of clear with this kind of an example why I don't like the term interaction free, because I completely agree that if we have an opaque object, I love the term interaction free. It's certainly interaction free in that case. It's just that most of the things that we're going to look at aren't going to be opaque objects that completely block the beam. It might be partially transparent. It might be an opaque object that's only partially in the beam. It might be a quantum object. And so I guess I prefer a more general term. And so we came up with the term quantum interrogation. I was thinking while I was here that maybe we could do quantum inquisition instead, and that reminded me of this is a graphic I have in my thesis that I drew. And this is why I'm not allowed to name things. We were implementing the Franzen experiment, so that was Kim Franzen controlling the rack. So I don't get in trouble for torturing Mother Nature. Okay, so then the question, of course, was can we do any better? And there were lots of long discussions in the Hofgarten with Anton Zeilinger and Mark Kasevich, and it really was true. He was the person who had we were all trying to think, are there ways that we can make it better? But he was the one who first had this notion: can we interrupt the coherent evolution? And so we started thinking about ways to do that. There was the picture from our from the 1995 paper of having some sense of what's a spatial mode Rabi oscillation from from system 1, which is the bottom system, into system 2, we're sort of slowly sloshing. But if instead we can interrupt that, we can keep knocking the system back into its original state. And as you go to more and more stages, then that gets more and more efficient. Now, actually, so the way I originally heard about the Zeno effect was in a popular article. I guess I don't remember where I first heard about it, but it was this idea by Asher Perez, which is a polarization equivalent of the Zeno effect. And so the idea is that we start out with, say, linearly polarized light, and it passes through a series of rotators. So, for example, it could be wave plates, but it's better to think of them as, I don't know, optically active materials or things that don't have a particular axis. No matter what the light polarization is, they will always get rotated as we go through them. So if I do this in n steps of 90 degrees over n rotation each time, then my horizontal polarization bends vertical and would not make it through this final polarizer. But if at each step I can continually project back onto the horizontal polarization step, then this is a trivial calculation to do that the probability of successfully making it through all of these is just going to be the probability of making it through one of them, which would be cosine squared of pi over 2n, and then I have to go through n of them, so then it's that to the nth power. So the probability of absorption goes like 1 minus this, and for n large, this drops like 1 over n. And so this is the curve that we see here. One thing that's a little bit disappointing, and I'm sure many of you who have studied this are familiar with, or at least as an experimentalist, this is not really falling very fast at that stage. So if you really wanted to go low, I mean, you need to have extremely high numbers of stages. And then the fact that each of these things is actually also absorbing in some sense, even if it's not supposed to be, that makes it not such a good thing. Okay, nevertheless, we thought it would be fun just to try and demonstrate just this. So this is kind of an aside on the quantum Zeno effect, just to do a clean demonstration of this. And rather than doing this with a whole bunch of polarizers, we kind of wanted to be able to do it with just one, a single, in this case, polarizer or polarization beam splitter. So we made this this kind of looping system here so that we can pass through a single element. Now, of course, we're passing through it in this case in 6 different locations. So one could say that it's 6 different elements, but it's okay. It was still, in this case, it was a single element. And we call this a photon cyclotron, and originally people arguing against that term, but really we are accelerating because the photon is changing direction at every bounce here, so it is an acceleration of sorts, even if it's not changing its energy. Okay, and so what we expect is that when there's no polarizing beam splitter in place here, the horizontally polarized light will become vertical, and I won't get any counts here, and if instead I put this in, I'll continually project on back into the original state, and that's effectively what we see. And so we were able to, in this case, basically preserve the initial polarization state, 60, 70% of the time, something like that. And this shows my own history, which is that I started doing these experiments in Innsbruck, and then I went to Los Alamos for a position for a while, and we repeated them and managed to get them substantially better from 60% up to 72% or something like that. So that's great if you want to detect a polarizing object, but the whole point of the interaction-free measurement was that we'd like to be able to detect an arbitrary opaque object. And obviously, if I put an opaque object here, well, I will detect it. I just won't get any counts on my detector, but that it won't be an interaction-free detection. So now the idea is to combine this sort of multiple interactions with the previous example that I had. Okay, so that was this paper from 1999. So we start out with a horizontally polarized photon, and it's going to make a number of loops in this large loop system, and each time it's going to make n loops. Each time we'll rotate the polarization by 90 degrees over n, and at the end of those n cycles, we will somehow switch it out of the system and then ask what the polarization is. So in the absence of anything funny going on here, the horizontal will become vertical, and it'll always be this detector. And then this is just the same thing that I showed before in the imaging case, where I break the incident polarization into its horizontal and vertical components, add them back up with the correct phase. So this has no impact on this stepwise evolution from horizontal to vertical, unless I block one of the arms. And again, assuming that I'm completely blocking the arm, then I'll continually be projecting the polarization state back into horizontal, and then I'll see the photons showing up there, indicating that there's an object present. And okay, so this is the same. This is a theoretical curve. We didn't do this with 50 cycles. So what this actually looked like in practice, it's interesting because this is actually not all that different, for example, from the system that Mark Kasevich was showing with their system, where they're trying to do repeated interrogation. So we do the rotation each cycle using a half wave plate that when we go through twice, acts like a quarter wave. We do the rotation each cycle by going through a quarter wave plate twice, going through it twice, looks like a half wave plate. The very first time we go through it, we only go through it once, so we have to sort of undo that with a pre-compensating quarter wave plate. And then we have a cavity, has a relatively high reflectivity, and we're actually able to change the reflectivity of this mirror. We switch in. So in some sense, we let the photon leak in, but then once it's in, it bounces around, undergoing this evolution. It starts horizontal, and then slowly it's going to start sloshing into the arm that would potentially have the object. And then after n cycles, we fire these pocket cells and quickly rotate the polarization, changing horizontal to vertical, and dumping out this port, or changing vertical to horizontal and dumping out the upper port. And then assuming that things are phase stable, everything will come back with the correct polarization, depending on whether or not there's an object in place. And so we did that initially with this lower reflectivity. So we actually have loss every cycle. And one of the things we notice is that, oh, well, we start to get improvement, but then the efficiency starts to drop as I go to more and more cycles. And as I improve the loss, so as I make this reflectivity higher, I climb up higher. But nevertheless, the point is these curves, because there's always loss inside the system, these curves always end up going back down. So we never actually asymptote. It's impossible to asymptote to 1 in this case. And any real system will always end up reaching a maximum and then coming back down. So that's pragmatic reality, I guess. In this system, we were able to achieve, I guess, 73% interaction-free measurement, and that was when we had our loss of about 4.5%. So, always need to come up with creative uses of these things. This was a Scientific American article that we wrote. So, one place where you want to see things with no light hitting them maybe is, Medusa is this mythological creature that will turn you to stone if you look at her, or if he looks at you. It's not always clear which of the two is required. But given that normally people often fight her by blindfolding themselves, if it were just her looking at you, then it wouldn't be that useful to blindfold yourself, I guess. I guess if you could blindfold her, you'd be happy. So one of the main reason I put this up though, is just to highlight one feature of this, is that the images that we get out are silhouettes of the original, right? So we're not really getting any information. We're not really getting any grayscale information. So, I used to tell people, and of course this works for any wavelength. So in principle, you could do it for X-rays. So you could go and you could get an X-ray of your body, and you wouldn't have to worry as much about getting X-ray dosages in you. And that's kind of true, but the X-ray that you would easily get would be one, the image would be similar. This was easier in the old days when we had transparency overheads. I just put my hand down and I said, this is what the X-ray would look like. You would just see the silhouette of your hand. You wouldn't see any of the internal structures. So not that useful. And so we did calculations of what does the efficiency look like, depending on how many cycles you have, and depending on what the single pass absorption of the material is. And if you go to more and more cycles, you can push the efficiency very high, no matter what the absorption is, even if it's not absorbing very much. If you go to enough cycles, eventually you can get this, assuming that there's no other loss in the system, you can get the fraction of interaction-free measurements to be very high. But it's important to note that if we plot the probability of an absorption inside the material, that is something that is also then achieving a peak, and it tends to peaks at around 2/3. And at one point I remembered, at one point I knew the explanation for why it peaks at 2/3. I no longer remember why that is, but it obviously happens. So this is an effect that people use. In fact, people know this in totally other contexts. So if you're trying to, for example, make a nanowire detector, a superconducting nanowire detector, and you want to have it be very absorptive, it itself is not very absorptive. So it has a very, not as high a single pass absorption as you'd like. You'd like it to be 1, but maybe it's only 0.6. But you can put it inside of a cavity structure, and if you put it in the right place, you get a resonant enhancement of the absorption of the thing you're trying to see. And so that it's I guess I would say this is not, in some sense, a new effect. People have known about this before. Okay. Looking sideways. So, other kind of strange applications of this. So, a couple of years after I had been at University of Illinois, so around 2004, I guess, I picked up this student, Honor Hostin, who was quite interested in fundamental sorts of things. And I said, well, we should see if we could do something more interesting, not just tech objects, but can we do something that would be connected with, for example, quantum computing, which is a big deal at the time. And there was a paper by Richard Joseph on how to do so-called counterfactual quantum computation, where you would put the computer in a superposition of off and on, and sometimes you'd be able to get the answer out. You could infer what the answer was, even though you didn't run the computer. And there were certainly some limitations to that, and that it only worked for some outcomes and only worked part of the time. And also in the original scheme, the overall probability of sort of inferring what the answer was not really any better than just guessing randomly what the answer was. So it's obviously not very useful for a computer. So the question is it possible, or by using more complicated schemes, because this was basically a very simple scheme that they came up with, to get it to work all the time and for all the outcomes, and the answer I would claim is yes. And then, is it useful? Maybe for error suppression. I guess I should put a question mark on the end of that. So just as a quick, what do I mean by a quantum computer in this case? So you can implement lots of quantum algorithms, all optically. If you can use multiple degrees of freedom of the photon to encode your qubits, and you have enough degrees of freedom to encode all of your qubits, then in fact you can do deterministic quantum logic with photons, which is great. You run out of degrees of freedom pretty darn quick, so this doesn't actually solve the quantum computing problem. But nevertheless, I do think it's a legitimate description of quantum computing. And Grover's search algorithm is this one where you have some unsorted database, and you want to find a particular element in that database. And if you use standard techniques, on average, you have to look at half the elements in the database until you find the particular one you're looking for. But Grover showed that you can get by with looking at only a square root of the number of algorithms. And in particular, if you have a database of 4 elements, it's possible with a sort of running it once with a single query, is a so-called Oracle-based quantum computer. With a single query, you can find the element. And classically, it would take with a database of 4 elements, classically, it would take 2 queries, one to sort of get what the first bit was, and then one to get what the second bit was, for example. Okay, so we implemented this. The details aren't really very important, I guess I would say, but we prepare a true single photon and we go into the algorithm and we're encoding these database elements with whether I'm going to put a photon in, whether I'm going to put a phase shift on, the output states that I'll read will be either a photon in mode A that's horizontally polarized, or in mode A that's vertically polarized, or in mode B that's horizontal, or mode B that's vertical. And then what the oracle does here is it puts a phase shift on one of these four states, and then you have to find which one had the phase shift. Okay, so this is what the algorithm looks like. So you send in a single photon, the oracle is set. The oracle in this case is a classical device, because actually implementing the oracle is something that I don't even think any existing quantum algorithms have done. That usually it's pretty hard to actually do a genuine implementation of an oracle in a quantum computer. Okay, so our goal was really basically just to find out which was the marked element, but only sending a single photon through. And the answer is that yes, okay, we're able to find the marked element with something like a 97.5% success rate. So actually at the time, this was, and for quite a few years after that, this was the best Grover's algorithm of any experiment that had been done. Okay, so that's where we were. That was back in 2000, and then now coming back to Onur Haston, who was going to try and combine this now with these to try and see if we could realize this counterfactual computation. And our first goal was just to implement it in a simple way, sort of Richard Joseph's scheme that didn't work all the time and wasn't perfect, but at least it was a thing we knew how to do. And Onur was busy setting it up, and he was also all the time thinking he could find some way that it would work all the time and you could detect everything. And I told him, don't waste your time with that. Don't waste your time with that, because it's Richard Joseph's a smart guy and he says it can't be done. And so fortunately, Onur didn't listen to me. He's very stubborn. And so he came up with a much more complicated way. So let's just quickly talk through this. So we have, for an optical quantum computer, I'm going to say that running the algorithm means you send a photon through the thing and the photon comes out. That's going to be running the quantum computer. I don't know what else it would mean for an optical quantum computer other than having the photon go through the device that's processing the photon. And not running the computer is going to be the photon going a different path, so it doesn't actually ever touch any of the optics that are running. And so we basically set up this interferometer around its typical, let's say Alice-Weidman interferometer around this search algorithm. And let's say that the marked element of the database is number 1. And that means that the photon is going to come out in mode A, polarized horizontally. And so we set up the system. It is this is like the no object case. So the system is set up that in that case, the photons always come out to this point. Okay. On the other hand, if the marked element was number 2, then the output is going to be photon mode A vertically polarized. So we can see already, because that photon is not going to make it to the final beam splitter, that now the second photon, sorry, the animations are a little screwed up, but anyway, the second photon can come to either output port. And similarly, if the output, the marked element is number 3, where it comes out in mode B, again, it's going to be effectively like blocking this path, or at least blocking the path before the beam splitter. So again, the bottom amplitude can go to both output ports. And similarly, if it came out in, if the marked element was number 4. So in this case, if we get a click at this dark detector, what we can conclude is that the marked element is not number 1. So we're able to at least say something about what the answer was. Not maybe as much as we would like, and it doesn't work with that high of a probability. Okay, so first let's work on getting these probabilities up. So at the moment, the probability is only 1/4. And so the idea is to try and push that up by using this xeno-type evolution. Right, I guess I should say this was the data of just that sort of single pass. And I think all I want to say is just, if the data is close to a line that's the line that it was supposed to be. So the theoretical predictions are the closest line to each of these. So basically we had a pretty good match with theory, so the whole thing worked sort of 94% of the time. Okay, but now let's see if we can push it so that it would work more often. And everything from here on in is only theory, not experiment. So these two interferometers together, this is the equivalent of the string of Mach-Zehnder interferometers, where we're going to slowly oscillate from the bottom half into the top half. So we're going to slowly oscillate from, this is a weak beam splitter. So the light is going to start propagating in the bottom half, but it's going to slowly trickle into the top half interferometer. So it will make multiple cycles there. So if we start off again with the condition where the marked element is number 1, where the search algorithm is going to basically leave the photon in mode A and horizontally polarized. So in this case, the search algorithm ends up not really doing anything. Okay, so the photon is kind of zipping its way around. And at the end, when I measure it, it ends up at this detector. So again, this is sort of like the equivalent of the no object case. But if it's not in number 1, if the marked element, for example, was a V coming out, well, now what happens, I've effectively blocked this upper interferometer. And so now when I do this, the photon is going to stay. Yeah, it's having a lot of trouble with the animations at the moment. It's interesting. I don't know why is it having so much trouble. Okay, that was maybe a little bit better. So instead of slowly sloshing from the bottom half into the top half, now the photon is going to get trapped in this bottom ring. And so depending on how many loops I do, assuming that there's no other losses, if I do enough loops, I can basically increase the probability of success from that 25%, up to something arbitrarily close to 1 if I can go to arbitrarily high numbers of cycles. Okay, so that was part of the problem. So part of the original problem is it only worked a small fraction of the time, and now we've been able to get it to work more often. So then owner introduced this other, so the other thing is that we would like it so that we can detect all of the possible examples. And so this is a more complicated scheme, and I'm not actually going to go through it in detail, except to say that when we go to this now a doubly nested Zeno effect, so it's a chained Zeno effect, what happens is that if the marked element is number 1, then the photon ends up showing up at this detector. And if it's not number 1, then it ends up showing up at this detector. So we're now able to, by sending, but in no case does it ever end up over here. So it never ends up leaving at any of the output ports associated with the quantum computer, so to speak. So if we go to enough cycles, we would say that the quantum computer itself is never actually running, but we do get information in some cases about what the measurement result is, or in other cases about what it isn't. And then you can make some changes to the system, which I probably don't show what they are here. Yeah, I guess I do. You can do some changes up here to the system that allow you to check the other possible measurement elements. So one by one, you can sort of cross them off as what the element was. So at the end of the day, then eventually you get to whichever one was the correct element, and you get definite information. So it is possible to find all the marked elements without the quantum computer running, so to speak, because the photon is not ever showing up over here. We definitely have lost the quantum speedup advantage because of the way we've had to do this sequentially. So Owner did do quite a bit of studying and looking into this, and he did find that in some circumstances, you could change the circuit a little bit, and you could come up with a scheme that protects against decoherence. that would work basically in cases when the photon is not absorbed. But I would say we don't have any general conclusions as to whether there's some generic error protection that might be possible with this scheme. I guess my intuition is probably no. There's probably not a generic error correction that we can do, because one error you might have is some sort of a phase shift. I mean, the way that we're encoding doesn't really have phase specific to it. It's if you're in mode A or mode B, it doesn't really talk so much about which phase you're in. But in any event, a real system that's implemented this way will have issues with phase, and then this is all sort of assuming particular phase. Okay, so that's all. That's what I have to say about counterfactual quantum computation. And then a couple of years later, people started talking about trying to do this for communication, and that was one of the reasons I had asked the question. Is it known that maybe it can help against some sort of errors or something like that? Okay, so I mentioned this at, I think, at dinner or maybe last night, and this is for you, Ben. You asked me to include this. So we did an experiment a while back. First, there was a theory paper with Andrew and Justin, and about how it's possible to make weak value amplification better by recycling the photons. And so the basic idea is that if we do a weak measurement amplification, which again people have been talking about, so I'm not going to go through it, but one issue is you get this amplification of the thing you're trying to measure, but that comes at a cost, because if you amplify by some factor f, it turns out you're only post-selecting. It's a weak measurement, so you're only post-selecting a small probability of the actual number of incident photons, in this case 1 over f squared. And so because the uncertainty ends up sort of going with square root of the number that you're looking at, it turns out that you don't really do any better than a classical sort of a standard measurement if the system is quantum noise limited. Now, of course, you're not always quantum noise limited. A lot of times you have systematic noise, in which case big win, something you should do anyway. But it turns out this is not a fundamental limit. And you can rely on the fact that if you're post-selecting and you're only pulling off a very small part of the wave function in this post-selection, this weak measurement post-selection, the rest of the state, if you didn't detect that, the rest of the state is basically identical to it was originally. And so now you can take that and you can apply the same weak interaction or the same small thing you're trying to detect and basically recycle it. And in this way, all the photons get the weak value amplification. So we did an experiment on that.
Excuse me, just a question.
Please.
So the resource here is the number of photons you have, or the number of times they go?
The resource is the incident number of photons.
Okay, so not the number of times they enter.
Correct. Correct. I'm saying that that's not a. Well, yes, I'm saying that that's not a cost. Obviously, it could be a cost if you're trying to get something happen more quickly. So that definitely could be a limitation. But you're defining the resource as the number of photons.
Okay, thanks.
Okay, so the thing that we were trying to detect was a small tilt of this mirror. And, of course, one way you could detect it is you could just have the beam tilted and go to a split detector, or in this case, go to a mirror and have it basically balanced so that about half of the photons are going to one detector, half to another one. And then as the beam tilts, you get more signal on one detector, less on the other one. So that'd be a way of detecting this. But instead, the weak measurement is that you make a superposition of the photons going clockwise and counterclockwise around this Sagnac interferometer. And you set it so that it's almost all the photons are going back out the way they came in. There's just a small fraction that's coming out the dark port. And now when you put a tilt on this, you actually get a bigger shift to the side. The weak value amplification leads to a larger lateral shift in the beam. And anyway, then that shows up on the detector. So that's the weak value amplification. And now the fact that the thing that comes back out of the interferometer is more or less the same as the thing that went in means that we can now recycle that. And so the way the experiment actually happened is that we start with photons. In this case, we were just doing it with an attenuated laser running at the 1/10 of a photon per pulse level, something like that. And we let the photons come in through this polarizing beam splitter. So initially the photons come in, they go into the system, they go both ways around this interferometer, mostly they come back out. And now when they're in here, let's say I take the transmitted one, now I'm going to fire this Pockle cell, and I'll just keep it on, and now the photon is, instead of being horizontally polarized, it's now vertically polarized, so now it comes back into the system. And similarly, the one that was the output of this, which was vertically polarized, it now becomes horizontally polarized and then comes back into the system. So this is sort of equivalent to this other interferometer that I showed, except it's a Sagnac version of it instead. So we can now have the photons cycling up to, I think we went up to like 30 cycles or something like that. So that now, to the extent that there's no loss in any of these other elements, then every photon eventually goes out, quote, the dark port. So you make a weak measurement on all of the photons, and that's a good thing.
So sorry, what is the error? I mean, you say that the non-cross selected wave function is almost identical. So it's not. I mean, there is some deviation.
There
what is the error introduced by this?
There is. That's true. And what you could do, what we did not do, but what one could do is you could take that through a just put it. So what does it do? You initially have a Gaussian shape, and what happens when you go through with this tilted beam is you etched out a little bit on one side. Yep. And if you keep doing that etching, then it will actually start shifting the beam. You can do a clever trick where you effectively, by having the correct number of reflections here, you have the beam that comes back in, you keep alternating which way it goes in, and so you end up etching off one side, then the other side, then the first side, then the other side, and you keep etching off the two sides, and so the overall shape that stays really effectively to first order, it's exactly the same as the initial state.
Okay, so what you're saying is that you will not have a systematic error, but you will have a broader distribution, nevertheless.
I don't think it gets broader. I think it keeps mapping onto the original state. Actually, you want to just comment on that?
Yeah, it just attenuates. So we calculate this explicitly in our theory papers. Yes, well, there are different ways you can try to reset this non-selected state. So one way is like the Zeno type effect, where you put it through a mode filter, but this flipping method works just as well.
The filter sounds good. And on new laser, it sounds even better.
Okay, so the results that we saw then, this was showing if we did a conventional measurement, it actually turned out to be one of the hardest things to get a really good conventional measurement in this case. Maybe I'll start with this one. As a function of the tilt of the mirror, kind of wish this were in angle and not in microns. But I don't remember exactly how to convert it into angle. Anyway, it was a small angle, and if you compare the multipath system, the signal that you get ends up being bigger, just because you end up having more photons, and so that gives you a better measurement of the tilt. And the signal to noise ratio, if you compare the single pass to the conventional measurement, basically those are the same. That's because we were operating in a quantum noise limited regime. But if you can instead do this multipass scheme, then you end up doing better. This is the same thing that Mark Kasevich was saying, right? If you can do this recycling, it ends up being a win. Okay, looking forward. So this is not something that has been done. It's something that I'm thinking about doing. So the idea is I'd like to perform spectroscopy, infrared spectroscopy, but I don't happen to have a spectrometer that is in the infrared. Certainly not one that counts single photons. It's always good to have a good acronym. I don't know that I'm going to stick with this one, but we just change it a little bit, and then oh shoot, it's blocked. That's no good. I can't have it be blocked. There we go. Oh, it's still blocked. Huh. Oh, that's because I have to do it on this computer. There we go, IFRIM. Okay, misspelled a little bit, but. Okay, so this is going to be, again, old experiment just to talk through how this works. So this is what Anton Zaling's group is working on kind of right as I arrived, so-called rail cross experiment. So I take a down conversion crystal and I pump it from the left and it produces signal and Eidler photons. And now if I retroreflect the pump, it produces them going the other direction. And now I'm going to retroreflect each of the signal and Eidler photons so that the modes overlap. So the modes of the photons created to the right overlap with the modes of the photon created to the left. And now we can just sort of look at what happens here. So the wave function then has a couple of different options, whether or not my photons were created going to the right or whether they were created going from the pump going back to the left. So if they're created from the pump going back to the left, then I'm sensitive to this phase of the pump from this mirror. And if instead the photons were created going off from the pump going to the right, then I become sensitive to these phase shifts that are imposed on the mirrors out here of the return beams. The point is that when I get a click at these two detectors, I can't tell whether they came from photons originally born going to the right or photons going to the left. And so those processes interfere with each other. And this is just put all of these up, just a demonstration of that. So this is looking at the, and they, I'll just say they interfere in a way that is, I guess it's not so surprising, I mean, once you see it, but you're actually seeing fringes not just in coincidence counts, but in the actual singles counts of these countings. That's kind of unusual, at least it was kind of unusual back then. Typically, people were only seeing things in coincidence, but this actually affects the singles rates as well. So if I change, for example, the Eidler mirror, I see fringes in each of the, all of the photons in the signal, the Eidler and the coincidences, and the signal and the Eidler were different wavelengths. And if I just change, for example, the Eidler mirror, everything sees fringes the same way. That's kind of got to be the case because I imagine that the fringes went all the way to zero. Okay, the visibility was not great, but pretend that they did go all the way to zero. It would be impossible to have, you know, a maximum for the signal and a minimum for the Eidler because the signal and the Eidler photon are always at the same time. So you can't have one of them be high and the other one be low. And then this is showing if you change each of the mirrors, what it does, for example, on the Eidler counts, and it becomes sensitive to whatever the wavelength of the thing bouncing off that mirror was, even if it wasn't the Eidler photons. Okay, so that was a demonstration of this effect. So this is like setting up the original interferometer that goes into the interaction-free measurement. Okay, so this is just the thing I just showed you, frustrated two-photon creation by interference. So it's frustrated if, for example, we're sitting at one of these nulls. And now I'm going to discuss frustrated two-photon creation by interference. So what I've done is if I put a block in this arm, well, then, of course, I no longer get the destructive interference because now there's only one way that you could get Eidler photons to go to this detector. So what we would then see, I don't have data that shows this, a little too bad, but basically we would not see fringes on any of these curves. In the same way that if you block one arm of the other interferometer, Ellis or Weidman interferometer, you don't see fringes. Okay, so there's one more step that we need, but you can kind of already see how this is maybe going to be. This is like a two-photon analog of the original interaction-free measurement scheme. Okay, so this was another paper that I was on in Anton's group, trying to turn the rail cross experiment into a quantum eraser experiment. And so the thing that we can do, if we put, so let's say initially everything is vertically polarized. That's what I mean by these the things going. This is the top view of the scheme. So polarized into the plane of the board. And now I put a quarter wave plate here, and so that changes this polarization to horizontal. And now the question is, will I see fringes anywhere? It's late on a Friday afternoon. You guys would all be able to answer this, I know, because you work in this field, but since it's late, let's just say the answer is that no, you don't see fringes anywhere. You don't see fringes anywhere. You certainly don't see fringes here because here you could certainly tell which path gave rise to this signal photon because you could just look at the polarization and you could tell which path gave rise to it. You also don't see fringes here. My students are sometimes confused by that. Why don't I see fringes here? But the answer, as I always teach this, is that if you could see fringes here, let's see, do I have an explanation for that? Well, okay, basically because this tells you could have made a measurement here that would have told you which of the processes took place, and that's enough to kill all of the interference. Okay, so this is going to be the starting case where I don't have any interference, and then
So
please.
what happens if you put a polarizer and project in only 45 degrees?
If you put a polarizer where?
At the red.
Right there. Great. So what happens then is that now I have erased the distinguishing information on this photon. So those fringes come back. The coincidence fringes come back. The fringes on these photons do not still come back. And this is the thing that I often explain to my students. These fringes cannot come back because this guy could be far, far away. And if these fringes came back by putting a polarizer in here or not putting a polarizer in here, then of course you could send signals instantaneously. And so we don't want that to be true. So and if you could work through the math, it also doesn't work. So the idler fringes don't come back, but the fringes in this arm come back. Okay, so now we're ready to solve the problem. Okay, so here's my scheme for infrared measurements. So I'm going to start with, for example, a broadband non-degenerate down conversion. It'll have a narrowband pump. So for example, a 532 nanometer pump could convert into a photon at 725 and 2000, or one at 650 and 3000, or 610 or 4000, or basically everything in between. So it's not meant to just be 3, it's meant to be a continuous distribution. Okay, everything is as I still had it set up before, so I've got this quarter wave plate here. Instead of having a polarizer here, I've now used a polarizing beam splitter where one port looks at the diagonal and one port looks at the anti-diagonal. And I'm going to adjust the phases so that any photons that come out here are all going to these detectors. So they're all showing up at this detector. And I should say also, I didn't really quite draw. These are single photon detectors, and it's meant to be after some sort of a grading system so that I can correspond each pixel on the detector with a particular wavelength. So it's set up so that assuming that all the light is coming back along this arm, then all the photons that show up all show up on these detectors. That's why this is flat as a function of the wavelength. But if I now have the substance in here that has some transmission as a function of these, say, infrared photons, where it reduces the transmission in this arm, that spoils or partially spoils the interference that comes here. And so I no longer have only unit probability of seeing photons here, or 0 probability of seeing photons here. Wherever I get these absorptions, I now get peaks showing up at this detector. So this is a way to do infrared spectroscopy at the single photon level without having an infrared detector. And in principle, I don't know, it might be actually quite significant. So we haven't worked through, I should say other people have looked into something similar to this, a little bit different in the way that they're doing it, but somewhat similar, and have been able to see somewhat encouraging results. I haven't done a full theoretical calculation in terms of Fisher information. I'll just say one other thing here. I added in this quantum eraser trick by putting a quarter wave plate here, and I wouldn't have needed to have done that. I could have just let the photons come back and just look directly at these, just using a rail cross experiment. And the reason I didn't do that is that, in general, there might be quite a bit of loss due to other things in this case, because this isn't necessarily like sitting right here. This might be going like a far distance away because you're trying to detect substances not very close to you. So you might want to have this be far away. There might be a lot of loss, and so you need to be able to balance that. And so by doing this quantum eraser trick, being able to sort of tune what basis you're in over here, you can get it so that you always have a starting condition of high visibility, and then that gets spoiled. So that should give you a better signal. Okay, so that's all the stuff I have to say. A final word. I was going to do this with ChatGPT, but I couldn't get it to work. So this is my own creation. Blame me or not. A final limerick. 93 to Israelis propose an effect that now everyone knows, often free of interaction, with great satisfaction. Quantum code mysteries exposed. So thank you for your attention.
Okay, great, Paul. Questions? Comments?
One minor comment on your last slide, there was a lambda 5, and there are only 4 lambda detectors. I guess you could probably swim the last one.
Oh, sorry. These lambdas?
Yeah.
Yeah, this is meant to be signal, signal photons. So this is meant to be the wavelength of any of these photons coming down. Yeah, you can't. S and 5 are pretty much indistinguishable.
Okay, good.
So
Go ahead.
So I have to do the mathematics, but I'm sure that you told already what it is. So assuming that you take the two items, I mean, after the mathematics from the nonlinear result, and doing a two-photon interference effect on the beam, what would be the result?
If you take these and you mix them on a beam.
Exactly.
Well, they'll act independently because they're totally different colors, and so they'll act.
Assuming that they have it, you go with the degenerate things.
Okay.
So they have identical what happens.
They're identical. Well, then if you have 2 photons, then they'll bunch. So they'll bunch.
Okay.
Paul, before you leave, I want to ask you a question. Suppose you have a partly silver mirror. You don't know whether it's half silver, quarter silver, and so on. And you want to know its transmission coefficients. You have a single photon, which for sentimental reasons you don't want to lose, you don't want to be absorbed. Can you do that?
So you want to measure the transmission with a single photon.
Yes.
And do you know it's like one of 2 values ahead of time, or do you not know anything?
You don't know.
Then
There is a paper by Yakil, Cohen, and myself shows how you can do that weak measurement with a single photon, which runs back and forth. So I'm saying it's
yeah, please. So I'd be very much interested in hearing that, because that's certainly something we tried. I had this value where we showed everything saturates at 2/3. So I'd be curious to know how to actually solve that problem.
Okay, so it's been a very long day, but I've been very stimulated by all the soul specialists. Thank all the speakers today that were